let's get on with the lecture for today. We're moving into groundwater, what I would like to refer as the dark side of hydrology. Most of what we've dealt with so far has been atmospheric, precipitation, snowpack, water balance. Anyway, kinds of processes that are a little bit more intuitive, easy for us to conceptualize because we see them. We see these processes around us. When it comes to groundwater, though, these are processes, it's an environment that's beneath our feet, and so generally not quite so esoteric. Sorry, not so straightforward and therefore more esoteric. And I find that this is where people start to struggle a little bit more with the concepts. There's a lot of new terms, and actually the last slide of this lecture is a glossary of terms related to groundwater. Yeah, lots of new concepts. This is a rather old graphic. I think this, based on 1996 figures. But what it represents is the reliance on the groundwater resource by regional populations. So for Canada as a whole, at least back in 96, approximately 30% of our water resource, municipal and domestic, came from groundwater. So that's groundwater wells that are supplying individual households and municipalities. But of course, there's quite a high regional variation, anywhere from a quarter all the way up to 100% reliance on groundwater. So if we look at the extremes, Alberta, incidentally, is the lowest reliance on groundwater, and Prince Edward Island, the greatest. Prince Edward Island is pretty small, and so they don't have major rivers. I mean, they have rivers, but they're not major rivers. They're going to be very much rainfall dominated. They probably don't have the land base to construct massive storage reservoirs. And what storages they do have are probably, like municipal water towers drawing from the groundwater. So yeah, that's a function of the regional geography. Its PEI is small. Whereas Alberta is a large land base and has a lot of snowpack and glacial runoff from the mountains, and all of that surface water drains across the prairies. And of course, the major urban centers, Edmonton, Red Deer, Calgary, Lethbridge, Medicine Hat, all of those major cities, that's where the majority of the population reside in Alberta. And of course, they're all on major river systems where they have a fairly, not exactly a perfectly stable supply of water, but at least a constant annual supply of river water. And you've got variations of those end members across the whole of Canada. And so that's why we see the variation in the reliance on the water supply. Multiple times throughout the lectures so far, we have referred to this change in storage in our water balance. And we have often stated that the change in storage is frequently considered to be associated with groundwater inputs and outputs. It's not 100% groundwater, and it's not always necessarily groundwater, but very often we'll think of the change in storage as being the change in the groundwater reservoir, which could be increases or decreases in water table. Okay, now that works over a long enough time period. So that's how we can relate some conceptualizations of groundwater to our basic water balance equation. So over a year or more, we can do this kind of thing. That's one way we can think of changes in groundwater. In this particular conceptualization, we're not that concerned with the actual processes that are going on. We just see it as something that we can't see, and if there's any discrepancy in those elements of the water balance that we can measure, then it must be due to a change in storage, which has a good chance of being a change in groundwater. Okay, that's one way to look at things. Now, over a short period of time, over an event, for example, a rainfall event, that doesn't work anymore because we know that the rate of transfer of water from the surface into the ground is going to take a period of time. But the time scale that operates on could be longer than the time scale associated with the rainfall event and the immediate runoff response. right? So now the challenge is that the processes act on different timescales, even though they may all be acting within our watershed. And to adequately account for the groundwater fluxes is a rather challenging thing to do at an event scale. Now, in hydrological models, of course, we do that. We do account for all of these processes in the real time of the simulation. But if we're measuring runoff output and precipitation input and estimating evaporative losses somehow, it can be challenging to adequately account for all of the groundwater processes within an event. So one way we often do that is we consider the groundwater to just be a loss. And I say a loss in inverted commas, because we're observing the rainfall, we're observing the output, but everything else that happens is just considered a loss. Now, it isn't necessarily a permanent loss. It's just a temporary loss in terms of how we relate the rainfall to the runoff output. Now, we're going to dive a little bit more deeply into these concepts later on in the course when we start looking at runoff generation processes and start looking at hydrographs. So that's all going to start next week. But for now, I just want you to get your head around this concept that groundwater processes can often be lumped into either a change in storage in the overall water balance, or they're often thought of as just a short-term loss from the rainfall to runoff relationship. These are two ways that we very often think of groundwater, but neither of those ways really explicitly address the processes that are going on under our feet. They're just hydrologically convenient. So just to recap, long-term water balance, groundwater processes can all be lumped into this delta S, this change in storage. Short-term processes on the event scale are very often just lumped into this concept of loss. They're just removed from the equation, not even considered at all, because they operate on a completely different time scale. Okay, now in the rest of this lecture, we're actually going to start diving more deeply into what's happening in the ground in terms of water storages and movements. We're not going to go into it in a great deal of depth because that would delve into hydrogeology, and that's a fairly in-depth course and set of materials in itself. So we're going to treat this quite superficially, but at least we're going to look at some of the basics. And of course, they all do relate to properties of the soils and the bedrock. So that's what we're going to look at now. Okay, so first thing to think about is what happens at the surface interface between the environment where we can see water on the surface and what's happening beneath. And so that process is infiltration. Now, when rainfall or snowmelt encounters the surface, the ground surface, then a number of things can happen. It can either infiltrate or it can run off. And in this particular example, what we've got is an environment where the runoff exceeds infiltration here, probably because the soil is saturated at this point, or because the rate of infiltration is less than the rate of rainfall. Whereas in this environment, we've got more infiltration because the water table is lower, the soils are not saturated, and the rate of infiltration exceeds the rate of rainfall incident on the surface. So we're going to revisit these concepts a little bit later on when we start looking at runoff generation processes in more detail. But I just want to introduce this notion that when rainfall or melt encounters the surface, it can either run off or it infiltrate. And whether or not runoff or infiltration occurs is a function of the soil matrix properties and the rates of those relative processes, the rates of infiltration and the rates of rainfall. Okay, and so what we're trying to do as hydrologists is partition these various components: precipitation, groundwater infiltration, evaporative losses, and runoff. So these are the processes that we're interested in, and for any particular event over any surface, there's going to be some differential ratio of all of those. So just looking at the soil zone in a little bit more detail. So once water has started to infiltrate, then we can start to think about the directions of movement. So infiltration is just simply the movement of the water from the surface into the soil. Once we've got water infiltrated into the soil, then we see percolation. So that's water movement through the unsaturated zone into the saturated zone. And then if the soil matrix is fully saturated, or if the infiltration rate is very slow, then we're going to get overland flow. Now, what should be apparent is that we are starting to introduce a number of new terms. So we've got infiltration, we've got percolation, we've got overland flow, we've got unsaturated and saturated zones. Now, that's one thing that's very common as we enter into a new stage in this type of a course, is that we've got new terms coming up. And so the very last slide is a glossary. And at one level, rote learning of terms is seen as tedious, and sometimes it's a redundant process. But actually, rote learning of definitions of terms can be quite useful, because if you understand what those terms mean, it reinforces your understanding of the underlying processes. So this is not going to be useful for you in terms of any of the labs, but in the exam, there will be a few definitions, because if you get the definitions right, then you probably understand the underlying processes. So I'd say there is value in this particular lecture in terms of going through the glossary and trying to understand what the terms mean, because some of these concepts are new, and looking at the definition of terms will reinforce the processes. So please do that. Okay, now a groundwater environment. So we have a cross-section through a hypothetical landscape. This is taken from the Christopherson textbook, Geography 1000 textbook. And what we can see here is a fairly homogeneous soil zone. I say fairly homogeneous because you'll see something that's very different on the next slide. We've got a groundwater table. We'll define that in a minute. We've got a number of rural households that have their own wells, and where they withdraw water from that groundwater aquifer, we've got a cone of depression associated with the well. So that's telling us that water is being actively drawn out of the ground, and it's taken some time for the water level for the water table to equilibrate. So if water was not abstracted from that well for a period of time, eventually that water table would equilibrate once again. We're seeing surface water interactions here. We've got a spring, and we've got groundwater interaction with a stream or a river here. So, of course, these are important areas for us as surface water hydrologists. I guess the one interesting thing here is that this spring is the result of an aquiclude. There's another term that's defined, or another term that needs to be defined. Aquiclude is a constraining layer within the soil or bedrock over which water cannot easily pass through. So the overlying material may allow lateral or sideways movement of water, but it may not allow vertical percolation because for whatever reason it's impermeable. And so as a result, any vertical percolation into that zone will eventually exit the ground via the spring there. So, sometimes that's just telling us that sometimes springs are associated with boundaries in the groundwater system or aquicludes, and that's quite common. Now we've got a slightly more complicated situation here. We've got some sedimentary strata. It's not a nice uniform homogeneous soil. We've got strata where we've got layers of different permeabilities, and as a result we've got confined aquifers. So for example here we've got two impermeable layers known as aquicludes, and we've got some sediments in between those two impermeable aquicludes, such that that creates a confined aquifer. And that confined aquifer, because it can't move vertically in this area, it's pressurized. Because here's the source water for this aquifer is over here. And so the water level, the water table is quite high relative to the regional or the local water table. And so consequently, the water in this aquifer is pressurized. So if you punch a hole through that confining layer here, then what you're going to get is artesian flow. You'll get pressurized flow such that water will rise up above the local water table and even above the ground surface if it's pressurized sufficiently. So that's how artesian wells happen. Usually because there's some kind of confining aquiclude and an aquifer becomes pressurized, and then there's some point at which it's vented or released to the atmosphere, and you see vertical flow. Okay, so let's look at things at a slightly smaller scale. Let's kind of zoom in a little bit. So here's a cross section. Actually, in groundwater hydrology, of course, you spend a lot of time looking at cross sections because it's easy to conceptualize the processes in that way. But of course, the processes themselves occur in 3 dimensions, or 4 if we consider time. So the cross sections are just a convenient way to look at things, but really we have to be thinking 3-dimensionally in terms of groundwater processes. So some more definitions. Vadose zone is the unsaturated zone above the water table. And similarly, phreatic zone is that saturated zone below the water table. But now, what is the water table? We all know what the water table is at one level, right? It's the boundary between the unsaturated and the saturated zone. It's where you're going to find a level in the ground surface such that if you were to drill a hole and put a well in there, a water level would equilibrate at the water table. Okay, that's in a general sense, that's what it is, and we all probably understand it that way. But there is a subtle level of sophistication to the water table that we really need to think about that becomes relevant when we start looking at different soil structures and thinking about tension processes or capillary action. And so the definition of the water table is that it's that level where the water pressure is at atmospheric pressure. Now, in fact, that point in the vertical profile where the water pressure is at atmospheric pressure is slightly below the zone of saturation. And the difference between the upper level of saturation and the elevation at which the water is at atmospheric pressure is known as the capillary fringe. And it can be very, very thin, centimeter or so, or it can be quite large, multiple centimeters. It depends on the soil conditions, but it's a capillary fringe. And so the upper boundary of the capillary fringe is saturation, and the lower boundary on the capillary fringe is the actual water table, where it's at atmospheric pressure. Now, to explain how that happens, let's think back to one of our earlier lectures where we were dealing with the basic properties of water. Now, remember, the water molecules are highly cohesive, right? They stick together very well, but they're also highly adhesive in that they stick to other surfaces very well. And so in an experimental or a lab sense, we can illustrate this by putting a couple of capillary tubes into an open bucket of water. And if we've got a tube with a very, very small diameter, we're going to see that water level will naturally rise up that tube to a higher degree than a tube with a wider diameter. And the reason for that is because the tension forces around the inside edge of that tube are sufficiently strong that they act to oppose gravity and pull the water upwards. So the narrower and narrower that tube, the higher and higher those tension forces or capillary forces can pull that water column upwards and therefore overcome the forces of gravity. Well, this is exactly the same thing that happens in a soil matrix. If you've got smaller and smaller and smaller pore spaces between small soil grains, then you've got the adhesive molecular bonding properties of the water molecules and the soil grains will act to oppose gravity and pull the water molecules in all directions, up, down, left, right, in all directions. But above the water table, that's going to act to oppose gravity and pull water upwards. And so those are known as tension forces. Now, I would have an entire lecture dedicated to this and what's known as matrix potential and gravitational potential and gravitational head. And I have a whole lecture dedicated to that, and that would follow on from this lecture. But I'm actually not going to go through that one this year because it would only manifest in the exam anyway, and the exam has been a little bit reduced. So yeah, unfortunately, you're not getting into that. But maybe Steph will talk about those things in 4400 next semester if anybody wants to dive more deeply into those processes. From a surface water hydrology point of view, they're not that important. But from a groundwater hydrology perspective, they're extremely important. Anyway, it's sufficient to know for now that water can move upwards in the soil zone against gravity. As long as you can accept that, we can move on, and that's okay. Again, a very important property of the soil or the bedrock groundwater zone is porosity. So it's often represented as N or as phi in this case, and that's the measure of the voids fraction from 0 to 1, or the voids fraction within the parent material. And so here you've got a few examples. So sands, clay, and bedrock. And we've got some numbers here. So 0.4 or 40% is what we can see here. These are well sorted, fairly rounded sand grains. Now, if we imagine those sand grains are very highly compacted, and now we've got different sizes of sand grains, well, now we can fill in those voids quite effectively. And so now we see a much lower porosity. Now let's look at clay. Now, clay is very interesting because we all probably intuitively consider that clay is quite dense, and we think of clay particles as being small, and we generally think of clay as not being very conducive to water movement. Well, it isn't conducive to water movement, but it's a little bit counterintuitive that the voids fraction or the porosity of clay is actually, or can be, quite high. So we can see here the example: poorly sorted clay particles, porosity of 0.7, more compacted clay particles, porosity of 0.5. So here we see clay porosity is higher than sand. Now that may seem a little bit counterintuitive, but we're going to look at that in a little more detail in a minute. And then bedrock, well, if you've got no fractures and you've just got a nice uniform slab of bedrock, its porosity might be quite low because maybe it's igneous or maybe it's sedimentary and all of the voids have been filled in. So its primary porosity, the gaps between the pore spaces, may be very, very low. However, with bedrock, secondary porosity becomes very important. Your secondary porosity is the spaces between cracks and fractures in the rock. So not necessarily the grains, but it's the porosity at a much larger scale. And so via those kind of cracks and pathways in the rock, you can get very highly porous bedrock materials. But in a granular sense, the porosity tends to be very low in bedrock. Okay, so that's porosity as a whole. Then there's this new term, effective porosity, or Ne or phi E. And now effective porosity is the porosity that facilitates or enables movement of water through the medium. Now, imagine you've got a big pore space in a block of soil or bedrock, but it's completely enclosed. Well, the porosity might be very high, but the effective porosity would be zero if it's not connected to any other pores. So really, effective porosity is a measure of the connectivity of the pore spaces within the material. And so here we have a plot that illustrates how porosity relates to water availability and how that varies between sandy and soil end members. So overall then, if we look at clays through to sands, clay, silt, sand, we see that porosity tends to be quite high in clays. So, somewhere hovering around 50% or more. Now that number is going to vary. This is just an example, but let's say somewhere around 50% on average. Meanwhile, sands may show a porosity somewhere closer to 40%. Now, as I say, this is just an example. In reality, you're going to see different numbers, but these are just approximate or average values. So that tells us sand has a lower water holding capacity than clay. Now, but that's not the same as water availability, because we also have to consider how much of that water is available to flow, right? How much of that water can readily move through that medium? Well, there's a big difference between sand and clay. The sand grains are larger, clay grains are very small. Therefore, the tension properties, the molecular adhesive capillary processes that occur in clay are very strong relative to sand, because the clay grains are very small. Therefore, those tension or those water holding processes are very strong in clay and very weak in sand. And so these molecular processes, these bonding processes, play a very important role in clay in not allowing water to move, even though it's a highly porous medium. And so this blue line illustrates that. So even though porosity drops from clay to sand, we see that the water availability, the water that can move, the fraction of the water that's available to move is much higher in sands relative to clay. So that somewhat explains the discrepancy between porosity and water availability in those two soil types. Okay, another term we need to wrap our heads around is volumetric moisture content, very important one. And this relates to porosity, of course. If we have a highly porous soil, then when that's, or it doesn't matter whether it's highly porous or not, but we have a porous medium, when that soil or bedrock is saturated, then the volumetric moisture content will be the same as its porosity, right? Because all of the pore spaces are filled with water. And here's a definition of that here. Theta, which is often used to represent VMC, is the volume of water divided by the volume or the total wet volume. The total wet volume is the sum of the soil, the water and air. So it's all of the material in that volume. A couple of other terms, which we'll look at in more depth on the next slide: field capacity and wilting point. So field capacity is the volumetric moisture content at which soil can no longer hold any more. It's the maximum amount of water that the soil can hold following gravitational drainage. So I think I gave you this example before. If you imagine you've got a sponge, you dip the sponge in a bucket, pull the sponge out, don't squeeze it, just pull it out, and then all of the water that drains out is gravitational drainage. What's left behind in that sponge is water that's held at field capacity. So it's held by tension forces within the soil matrix. And then wilting point is even drier, even less moisture. Now you can imagine you've kind of wrung it out a little bit. And that's the minimum water content where plants can extract water. This is where you've got competing moisture demand from the soil molecules that are trying to attract water molecules to the soils, and those adsorptive processes exceed the osmotic processes of the roots trying to also draw in water. So it's all tension processes, but basically it's like a tug of war between the soil and the plant, and the soil wins. At moisture content below wilting point, that's where the soils have won, and the soils hold the moisture and plants can't extract them anymore. It doesn't mean there's no moisture there. It just means that any moisture there is firmly bonded to the soil grains and cannot make it into plant roots. And so again, I've shown you this diagram before, but this is just the example again. Here we've got zero moisture content. Not exactly a realistic scenario. You might get it in dry deserts, but usually there's some moisture affiliated with soil grains, even if it's just molecular. Then we've got low moisture content. Here we're in between wilting point and field capacity, and here we've got high volumetric moisture content, and which is going to max out at porosity. So if porosity is 50%, then VMC will not exceed 50%, right? Because it's at porosity. Often you'll hear terms like 100% saturation. Now 100% saturation is not 100% volumetric moisture content, because volumetric moisture content cannot exceed porosity. But 100% saturated it means the same as VMC equals porosity. Yet another cross-section. So this is similar to a slide we've seen earlier. We've got our unsaturated zone. Here we've got our capillary fringe. So here's our saturated zone above the water table. But what I want to illustrate here is how this relates to VMC, or volumetric moisture content. So up to the capillary fringe, we're saturated. So this is porosity, or the porosity and VMC are the same thing up to this point. As soon as we get above the capillary fringe, we see that the volumetric moisture content decreases. And then once we're into the the soil zone where we've got root activity, then we start to see that the volumetric moisture content reduces even more. And that's partly because of root, like osmotic root processes. But there's also one other process that's active at the surface. Can anybody tell me what that is? So we've got competing demands for soil moisture. Tension processes in the soil. We've got roots trying to pull in water, but there's one other process that's active and is impacting the moisture content.
Would it be evaporation?
Exactly. Yes. Perfect. It is evaporation. So the evaporation is clearly going to be active on the soil surface. And if you've got air spaces in the soil, it's also going to be, there's going to be molecular diffusion from the liquid to the vapor phase, also carrying on in the soil. And so clearly that evaporative demand is going to be maximized near the soil surface, where it's easier for those latent heat processes to escape into the atmosphere. Obviously, as you go deeper and deeper into the soil, then evaporative losses are going to diminish. But close to the soil surface, evaporative demand is high, and that's another reason why you see moisture content tend towards zero at the soil surface. So that's one thing to bear in mind. You've got tension processes, you've got gravitational drainage processes, you've got evaporative processes, you've got root processes. All of these things are driving soil moisture movement vertically and laterally in the soil zone. Okay, so now that we're starting to think about movement, let's think about groundwater mobility. And one of the terms that we use to describe the ability of a soil matrix to allow water to pass through is permeability. So permeability is just a measure of whether it can or can't allow movement. It is not a measurement of the rate of motion. That is hydraulic conductivity. So conductivity is the coefficient of permeability, and it's expressed as a velocity measure, typically meters or millimeters per day, something like that. And that's K. So if you come across K, it's almost universally K, conductivity. And here you can see an example of how for any given hydraulic gradient, which is analogous to the force pushing water through the soil, very often set up by a pressure differential in the soil medium. But for any given hydraulic gradient, the conductivity of clay is going to be a lot less than the conductivity of soil, even though the porosity of clay is higher than soil. Again, those molecular adhesive tension processes prevent motion in a clay soil. They don't stop it, but they slow it down. Okay, so just to summarize some of the flow pathways then. So above this is a hill slope, cross section through a hill slope. In the unsaturated zone, we've got infiltration at surface. We've got percolation into that zone. So infiltration percolation processes tend to be vertical. We have capillary rise above the water table. That's due to the tension processes in the soil zone. And then we're also going to have gravitational drainage down, but also laterally if the structure in the soil allows for it. But usually gravitational processes in the unsaturated zone are vertical, usually. We start to see lateral flow more in the saturated zone, and this is because of differences in pressure. So for example, if we look at the water table here, so the water table is higher here and lower here, therefore there's going to be a higher pressure here relative to here, and it's going to move the water along that pressure gradient. Now, again, these concepts of pressure gradient forces are something I'm not going into in today's lecture. That would be in the next lecture that we're not going to cover in this course. I will upload the lecture so that you've got it, but we're not going to be examined on it, and I'm not going to touch on it in a lot of detail. But yeah, anyway, pressure gradient is going to lead to motion within the saturated zone. And all of these properties are going to influence the motion. So soil permeability, clay fraction, of course, are going to slow things down, whether the soils are frozen or non-frozen. So a frozen soil, for example, it can create like aquiclude conditions. So in an earlier slide, we looked at aquicludes and thought of them as like highly compacted sediments or as different types of bedrock, right? We can consider an aquiclude as a permanent confining layer in that situation. But also we've got seasonal confining layers. When the soils freeze, then they disallow water movement in the groundwater zone. Very important when it comes to infiltration processes. And of course, land uses. You know, if we get compaction of the soils, that's going to alter the infiltration rates. It's going to alter soil water movement as well. Okay, now, actually, let's just look at this conductivity that we see here for soils, sandy soils and clayey soils is typically measured over a cross-sectional area within a soil medium. And it is assumed that movement across that cross-sectional area is uniform. So it's assumed that we have like this diffuse wetting front or this diffuse homogeneous movement of water across this cross-sectional area, this theoretical surface within the soil medium. In reality, of course, the movement of water around soil grains is very tortuous, as you can see in this diagram here. So here's our soil matrix. The movement at a particulate level is not straight. It's very irregular. But when we're defining hydraulic conductivity, we're assuming it's straight through a cross-sectional area within that matrix. So hydraulic conductivity as a rate of motion does not describe the rate of molecular motion. It describes the mean rate of motion across some cross-sectional area. Okay, now hydraulic conductivity is very useful in that regard because in theory we can scale it up, right? We can scale from 1 meter squared within the soil zone up to very large areas. You know, we could scale it up to some regional level if we knew that our soils or bedrock were homogeneous over a very large area. Okay, that's a nice theory. And in practice, we do that. We do utilize hydraulic conductivity in that sense. But in reality, we have to accept that we have preferential flow pathways. Not all of the flow within the soil or bedrock behaves according to these matrix flow conceptualizations. So this is where we have to consider macropore or pipe flow. There's lots of examples for how that can occur, but you can think of root systems in the soil. You know, roots die, they leave gaps, they leave little tunnels in the soils. Worms, burrowing animals also create pathways through the soils. Soils crack You know, they dry out, expand, shrink, and they crack. And so all of these discontinuities in the soil zone or in the bedrock zone, if we're dealing with cracks, relate to preferential flow paths that are going to bear no relationship to the matrix flow that we describe using K, or hydraulic conductivity. So as groundwater hydrologists, then we have to be aware of those potential preferential flow pathways. And one way you can do that is, you know, instead of having your nice 1 meter squared area over which water is flowing homogeneously, you might want to re-evaluate the scale at which you estimate K to be something much, much larger, several meters, tens of meters, hundreds of meters squared. And now you redefine K for that larger scale. So that doesn't mean you can't use hydraulic conductivity as a concept. You can. It just means your estimate of K, the number that you use to define or quantify hydraulic conductivity, is going to be very different at different scales. Okay, so hopefully that makes sense. You've got a matrix flow set of processes described by one value of K, which works at a very small scale. Then at a much larger scale, you've got macropores, preferential flow paths. You can still use K, but the K in those two situations bear no relationship to one another because they're describing fundamentally different processes. Now, even though I've gone through that very, very quickly, this is one of the fundamental challenges in hydrology when we're trying to describe flow in a groundwater environment or in a watershed as a whole. K is a very useful term because it allows us to define the rates of flow through the groundwater system. But depending on our scale of interest, how we quantify K is going to be very different. So this is one of the conundrums in hydrology. Lots of papers written on it, lots of time spent on it, and we've just glossed over it very, very quickly. Now, as an illustration, where we're going to finish off in this lecture is infiltration, how water gets into the soil. But as an illustration of how preferential flow pathways play a role in modifying the rate of flow through the soil medium, we got three examples. I apologize, I forget which textbook I lifted this from, so I don't have a link for you. But anyway, they serve a good purpose. We've got a relatively uniform wetting front here. So you can see three dyes have been introduced, or dyes have been mixed in with water. Water has been poured over the surface, and then we've cut a cross section through the soils. So in this case, we've got a fairly uniform sandy soil, and you can see that the dyed water is, you know, infiltrated relatively uniform. It's not perfectly uniform, but at least it's laterally covered that entire zone. Now, this environment, I don't know what that is. It looks like silts to me. I can't be sure, but there's definitely some sedimentary layering in this soil zone. So it's probably silty lacustrine deposits or something like that. And in this case, you can see somewhat uniform infiltration, but then we start to see spreading out along these horizontal layers within the sediments. And you can definitely see that here, where we've got a kind of a boundary or discontinuity in these sediments. And you see the water starting to travel laterally along that boundary. Now, in this situation, we've got a soil that has dried out and expanded and cracked and gone through various cycles, probably got a high clay content to it. And so now what we're seeing is we've got very distinct cracks, mechanical failures in the soil, and they've led to very distinct preferential flow pathways. So in this case, even though the dyed water was introduced at the top, it hasn't infiltrated into the soil matrix at all. So there's no matrix flow here visible. It's all preferential flow down cracks. So here it's 100% matrix flow. Here is mostly matrix flow, but then some movement across discontinuous boundaries. And here it's 100% preferential flow. So hopefully that illustrates the difference in matrix flow and preferential flow. And in this particular case, it's related to infiltration, but that also applies to flow throughout the soil medium in general. Even in the saturated zone, you'll see those flow behaviors. Right, okay, well, we've still got 5 minutes, so this is a good place to end. I'm just going to end with an example, calculation example for the rate of infiltration. Now, believe me, this example is absurdly simple. In reality, the examples would probably be a little bit more complex, but the purpose of this example is just to get the general idea. So we've got some rainfall that's falling on the ground surface, and it's a certain amount has fallen within a certain time interval. So we'll call that T1. And then here's our groundwater, our soil matrix beneath this. So here's the surface, here's the rain incident on the surface. And this is after a certain period of time, all of that water is infiltrated. So for this particular example, we've got a dry soil matrix, or relatively dry. It's got some porosity and ability to accept new water. And by T1, all the water's fallen on the ground surface. By T2, all of the water's infiltrated. Now we can calculate the depth of infiltration as a function of the depth of precipitation divided by the effective porosity minus the volumetric moisture content. So remember, 100% saturation would be when the volumetric water content equals porosity, in which case there'll be no ability to infiltrate. Then we can calculate the effective infiltration rate as the observed infiltration rate at the surface divided by the same thing, the effective porosity minus volumetric water content. So here we have an example. We've got 2 millimeters of rain falling, and all 2 millimeters infiltrates to the soil within 1 hour. Okay, well, instantly we know that our rate of infiltration observed at the surface is 2 millimeters within 1 hour. A real world example would probably be a little bit more sophisticated than that. But anyway, the observed infiltration rate at the surface is 2 millimeters per hour. We have a porosity of 35%. In this particular example, it doesn't matter whether it's effective or general porosity. They're the same thing in this example. And we also have an initial volumetric moisture content of 15%. So there's already some water in the soil matrix. It has a 15% volumetric moisture content. So, we have to account for that when we think about how quickly that water is going to infiltrate into the soil. So the questions then, what is the depth of infiltration in millimeters? What is the effective infiltration rate in meters per day? So we already know it's 2 millimeters per hour, but what is it in meters per day? And then what soil properties would speed up infiltration? If there's a silt soil, what soil type would infiltrate more slowly? So we've got 3 minutes, and I know you could probably all look at the next slide if you're on Moodle, but does anyone want to answer those questions for me? The maths is pretty straightforward. No calculus or trig here. Okay, anyone want to answer any of these before we break up in 2 minutes? Any of these questions?
Would a higher percentage porosity increase the speed of infiltration?
Yep, it would. So if we've got a more, well, actually, no, not necessarily, because think of the soil, the sand to clay example. The higher porosity would mean our depth of infiltration would decrease, but it doesn't necessarily mean the rate of infiltration would increase. In this particular example, we already know that our depth of our rate of infiltration is 2 millimeters in 1 hour. So this one is just a unit conversion from millimeters per hour to meters per day. But porosity it's fundamentally important. Yes. Anyway, so clay would infiltrate more slowly, even though its porosity is greater. Okay, anyway, let's look at the numerics while we've got 1 minute left. Sorry, I could have done with a bit more time on this. I urge you all to kind of look through this on Moodle and just make sure it's clear in your head. I hate to rush through anything that's calculation-based, even if it is a very simple calculation. But so applying this calculation here, depth P over porosity minus volumetric moisture content. Our porosity is 35%, our VMC is 15%. So therefore, the net of those two is 20%. So we've got a 20% volume that contains air or space for additional water. And we know we've got 2 millimeters of precipitation. We know we've got an infiltration rate of 2 millimeters per hour. Therefore, the depth of infiltration is 2 millimeters divided by 20%. So it's multiplied by 5. 2 millimeters times 5 is 10 millimeters. Effective infiltration rate of 10 millimeters per hour is the same as 0.24 meters per day. And that's simply because we've got the millimeter to hour conversion and the hour to day conversion. So that should be hours, not meters. Millimeters per hour to meters per day. So millimeters to meters, hours to days. It's just a simple calculation. Okay, anyway, sorry, I rushed through that really quickly because it's 1:15 right now. But that's this lecture. Please go through that last couple of slides though to make sure you get that one. You never know, I might have an infiltration question on the exam. It'll only be worth 1 point, but every point's worth it. Okay, thanks everybody. I'll see you next Monday.